Hi, hello. Welcome everybody. Today I have a pretty long presentation talking about introduction of the simulation of an inverter in terms of EMC. So originally I did this for our webinar with the SolidWorks friends of us, but it was in German, so that's why I have decided to do a second recording now in English, so it's better accessible for you. So probably it will be 30 to 40 minutes today, but I think it's quite valuable input to understand the EMC behavior of an inverter. So let's start with a little bit of an introduction. Of course, why inverters? Because the simple answer is because they are almost everywhere. In the recent years, you see power electronics in inverters, of course, being very prominent in electric vehicles. But it's not only limited to electric vehicles, of course, for air conditioning, for pumping, for industrial motors, for railway applications, even in drivetrains of a train. You find inverters, and also on the regenerative energy side in solar inverters, like when I'm thinking about having a solar panel generating AC power, you're using inverters for this. Also in wind turbines, so there's a very wide application and also a very different range of scales for inverters. And that's why it's particularly interesting to look how they behave in terms of EMC, because as always, every product on the market has to satisfy the EMC limits. And we will talk mainly about conducted emission today because I think it's a little bit simpler. But of course, radiated emission is also controlled via EMC limits and can also be simulated. But let's stick first to conducted emission. So what's typically done is, of course, you DUT, the inverter will emit some noise due to the switching. And this noise might couple into the power supply. That's why we need to make sure that the level of the coupling of the power supply, being it like the power supply system in a vehicle, but it could be the power supply in your house, this has to be limited. And how that's typically done is that you have a so-called LISN, a line impedance stabilization network, through which you connect the power source of the inverter. And this LISN, it has an output to an EMI receiver where you measure the emission, and then you are comparing the emission levels to certain limits, which can be different, but in the end, it's always comparing in some frequency bands against a maximum value. And you make the EMC test if you are below the value, and you fail, of course, if you are above. So typically how we do things in EMC. And when we look at a typical inverter, so here's a kind of system schematic. So you see we have the source on the left-hand side, and this listens, we couple out to the measurement. Then there will be some cable which connect to this light blue box, which are called, that's the power electronics. So you will typically have an input filter, depending on your source, a rectifier, which might be required, like when you have an AC source. Then you will have typically a power factor correction, depends also again on the inverter type. And then, of course, you need some controls of the inverter, which will typically be some low voltage electronics. So you would require another converter to down convert the voltage to provide this voltage to the control chips. A DC link capacitor to provide like short power to the inverter. Then the inverter itself and a cable going out to the motor. And here you see this capacitances to the ground, which we will see later on have a very important influence on the emission of an inverter. We will start, of course, a little bit simpler first. So first of all, the controls will assume a fixed load and a fixed operating condition, a fixed PWM signal in the end. So we will not include the controlling in the EMC simulation. It's typically not done simply because would make the simulation a little bit too complex. So we start something really where we use a fixed operating point basically, and I left out all of this on the left hand side. So even like a converter or a power factor corrector, they might be also important for the EMC behavior, but I will not cover this. It's our introductory course. We will talk in this introductory course about the inverter itself. So I built a simple circuit model of an inverter. That's how a typical three-phase inverter would look like. So again, the source as we had before, some listens on the circuit, and this three-phase H bridge, which driving a certain motor. It's a very typical setup for an inverter simulation. And I'm doing all of the simulations, of course, inside CSD Studio, as I'm always doing. Just to mention here, so of course in CSD Studio you also have a circuit simulator. As you can see, here's my inverter inside the circuit simulation, and we will typically run transient tasks to include the full switching of the inverter. So that's how typically such an inverter switches. So I have just two phases shown here, the third phase just not there because there is no space on the slide, but of course all three phases will switch with a so-called pulse width modulated signal, so short PWM. And these PWM signals typically are in something like double-digit kilohertz range, so 10 kilohertz, maybe 20 kilohertz. That are very typical values. And with this PWM signal, if you apply the signals to all six transistors of your H bridge, what you in the end will get is kind of sinusoidal signal going out to the motor to generate the rotation of the motor. And I have chosen, so that's actually what I mean by the operating point. So I choose 10 kilohertz for the pulse width modulation and 300 hertz as the sinusoidal signal going out to the motor. And depending what kind of PWM you apply, you can, of course, have different values here. You might have a different PWM frequency or a different value of the sine going out to the motor, because that's actually the frequency which is linked or is proportional to the rotational frequency of the motor. But it does not mean that at 300 hertz you will have 300 rotations of the motor in a second, because it depends on the topology of the motor, how many poles you have and so on. But I'm not a motor expert, I'm not talking about motors too much. We talk about the power electronics section. So the first thing is, of course, we need to ask ourselves, where's the noise coming from? What's leading to the EMC emission? And that's a very obvious answer. The switching of the transistors is the main source of the noise. Simply all of these transistors switch the current very, very quickly on and off. And this is noise. And because for efficiency reason, actually, you want to switch as fast as possible, because this will reduce losses in the transistors. But of course, the faster you switch, the more harmonics you will get, which will lead into increased emission or higher EMC. And this is why it's a little bit like the efficiency requirement is typically contradicting the EMC requirement. But in the end, we all know that efficiency in electric vehicles, when we think about electric vehicles, efficiency will always win. That's why the task the EMC engineers to control the emission even for very high switching frequency, and that's our job. So we know now the switching of the transistors is the main source. And before talking about how the switching now propagates to the listen and to the position where we measure it, we do a first step by dividing the emission into two different modes. It's the differential and the common mode. Even the measurement is done single-ended. So in the measurement, what you do, you measure P versus PE, and you measure N versus PE and compare it to the limits. But in order to understand which filtering is required, we first separate the emission into differential and common mode. So differential mode means you have a voltage between this P and N lines, the supply lines. And common mode means that both supply lines have a voltage against PE. So PE stands for protective earth here, which might be the chassis of a car or a third wire. It depends. So why we do this, we see because both of these modes has a different way to propagate and also different countermeasures. And this is why I do this division here. And first of all, let's look at the so-called differential mode loop, right? So the switching of the transistors. Now, of course, every transistor switches. I'm just sketching here the propagation of this differential mode for one particular transistor. All of this transistor will have some kind of path, but the path will always look like this. It's going through the motor through the low side, and then we measure a voltage basically between these two input lines. That's what we call the differential mode. Simply you are switching in here, you are switching here on and off. So you are having this arm and basically this bottom arm where the voltage is applied, where the switching is applied. And that's what's generated the differential mode loop, and it propagates over the two wires. Well, for the common mode loop, it's we have to add now this protective earth. Of course, I said that the two wires, they have a voltage against PE, right? So we have to include PE into the picture. And the PE is, of course, isolated from the electronics. That's its job. But there will be some parasitic coupling, namely capacitances. There will be capacitances in the motor. There will be capacitances from the board to PE and also from the cables to PE, so that the propagation of the common mode will mainly happen due to this parasitic capacitances. And you see it's drawn here. So these two arrows now point in the same direction, while this one points in the other one. So we have basically a voltage between this arm and the PE arm. And looking already at this, it's a very general rule saying like at the low frequencies of the switching, the differential mode will typically be higher than the common mode, while at high frequencies, the common mode typically is higher than the differential mode. It's kind of rule of thumb, of course, because these capacitors, at lower frequencies, they will have a high impedance, while at higher frequencies, this impedance decreases and more of the common mode emission will be present. And we will look in this now into detail. So taking again this bridge schematic as I shown in the beginning, and I'm running a switch simulation with the same PWM settings as shown in the beginning, and always evaluate the differential and the common mode basically on these two listen circuits. And for this completely symmetric model without the capacitances to ground, we see it's clearly the differential mode, it's dominating. Basically, there is no path for the common mode here, so there is some noise still appearing here. It's not perfectly zero. On the circuit simulation, it's not perfect, but you see that something like more than 90 dB differential mode here at the low frequencies compared to the common mode. So that's as we would expect. In such an arrangement, no common mode basically exists, and this is the result we are getting. So that's clear. Now the first question is, what do we do with the transistors, with the switches? Actually, I mentioned the switches are, of course, the main source of the noise. So that means depending on the behavior of your switch, your emission might change quite significantly, depending just how the switch behaves, because a switch is typically not perfect, right? It got some, you will use a transistor. Let's keep MOSFETs here for this case. The MOSFET will have some capacitance between drain and source and so on. And what I did here, I have just simply used a different switch model. And you can see that changing this switch model can significantly change this emission. You can see the second switch model, which is gray down here with what I call a generic MOSFET. It shows just a higher emission levels here. And it's important to note that if we want to have accurate simulations of an inverter, we have to make sure that the switch is doing the right thing. Of course, sometimes we get the switch models like SPICE models from the vendor of the transistors, but they are often not optimized for EMC performance. So sometimes we have to, if we want to compare really simulation and measurements, we need to be aware that the switch model needs to deliver the right result. That's very important, as you can see also here in this example, but also in more advanced studies where we compare simulation and measurements, we know that the switch model is really important. One first thing when we talk about EMC, what you might do is, before going to the step of filtering, is to apply a so-called snubber circuit. So you can see here, this is a so-called RC snubber circuit. So I have a resistor and a capacitor basically between gate and source of the transistor, and it can dampen or it can improve your EMC emission simply because what you do is you create a path for this higher frequency behavior, right? So if you're switching with 10 kilohertz, of course the low frequency current, it has to go to the motor. It's required to drive the motor. But for the high frequencies, let's say maybe in the megahertz range or several hundred kilohertz, you want to keep them. It's always a good idea, or what's always done in EMC in order to improve your EMC behavior is to keep the current loops as small as possible. That's a general rule. So by adding this capacitor and this resistor here around the transistor, I make sure that already the high frequency current loop might stay very closely confined to the circuit around the transistor and reduce this emission. Of course, it doesn't work for all. It's not a perfect thing, but it's something which is typically used, so it should be mentioned here. I don't have a plot showing the influence, but a snubber circuit is a first way what you could think about when you want to improve the emission from an inverter. Then what we need to take a look is, of course, our components. So I have used a capacitor, a DC link capacitor with 100 microfarad. And in the first simulations on the previous slide, the capacitor model was ideal. So it was a perfect capacitor, and we know that capacitors are not perfect. A capacitor, due to the connection to the rest of the circuit, will also have some kind of parasitic inductance. And the bigger the capacitor, again as a rule of thumb, the bigger the capacitor, the higher typically this connection impedance, inductance and impedance. So what I've chosen here is I have now a model of the capacitor. It's still the same nominal value. It's still 100 microfarad. But I have added a 3 nanohenry in series and 1 ohm in series, so that the overall impedance of the capacitor is of course now different. So in the ideal impedance, it goes down basically to infinity. You have very low impedance, but that's not true for a real component. And changing just the behavior, changing just this capacitor to include the parasitics, we can look now again at this differential mode emission, and you can see this has a huge impact, especially in the high frequency range. We have something like 40 dB difference simply because the capacitor is not ideal. So the second step, if you want to simulate the emission from an inverter after the switch model we had on the previous slide, it's important to include all of your components as parasitics. Ideal components will not give you the right response. As you can see how drastic the change is just by adding this parasitics of this capacitor. So that's the next step. Let's continue. And up to now, what I had was just the differential mode. We didn't have this capacitances towards the PE part, and now I'm adding them. And of course, I'm just guessing them. I'm doing an educated guess what might be a typical capacitance, and I added 3 of them, right? So I'm adding like a capacitance from this, basically from the plus, from the positive input to the ground, from the negative input to the ground, and from the motor to the ground. And you see the values they don't look that mighty, right? It's picofarad, 3 picofarad, 12 picofarad, and 10 picofarad, which are guess value, and we will see later how we can do a much better estimation using simulation. But here I just choose them as typical values. And now we can see adding this capacitor doesn't change anything on the differential mode, as we see here on the top. This is basically the same spectrum. However, now as obviously the common mode, which was not able to propagate previously, now by adding this capacitors, the common mode jumps up by something like maybe 50 dB here. And again, saying that at this low frequencies, the differential mode is typically larger, while at high frequencies, the common mode is larger. In this example, it's not as clear, but that's what you will typically find in real hardware. So this is, of course, a simplified example. And obtaining this parasitic capacitance, which I just guessed here, I will show you later on how we do it. So now we have a path for the common, and we have a path for the differential mode. Let's think, how can we filter this? How can we make sure that this emission doesn't reach the listen, right? We want to keep the current confined to the system with the power electronics. So that's where we add a filter, typically an input filter somewhere at the power electronics, where you connect the power cable to the rest of your system, to your power electronic systems. And talking about filters, I choose, of course, the most simple one, kind of pi filter. So I add 2 capacitors between P and N, and between these two capacitors there's an inductor. It's a very high inductor value, 100 microfarad. Probably you wouldn't use it in the filter, but I chose it because it clearly shows what's happening. And these both capacitors are 3.3 microfarad, and they have also some parasitic value. So I'm adding now parasitics really also to the filter. And with such a filter, of course, we see this pi filter can only have an effect on the differential mode, right? It's placed between these two wires, between the P and N wires, so it can only work on the differential mode. It will not have any influence on the common mode. And that's also what we see in the spectrum calculated here on the left-hand side. You see the differential mode now, of course, mainly because due to this huge inductor, it dropped over the whole frequency band. A high frequency with excellent filtering. At low frequencies, of course, is a little bit more challenging. And the common mode has been also affected slightly here. This is, again, it's not of these things are perfect. The common and the differential mode is not like a binary thing, like it's there or it's gone. So there is always some transition between these modes. That's why you see also some effect, but it's rather slow. I mean, the effect of this pi filter on the common mode is much slower than on the much smaller than on the differential mode, as we see here, and also in the low band, basically nothing happens. So that's what a pi filter can do. It can filter your differential mode. It can also, you have to be a little bit careful because this inductor, it introduces, let's say, an asymmetry. So it might lead to also a differential to common mode converted simply because your filter is not perfectly symmetric. I have placed just this inductor into the P line. You might also place a second inductor here, but it's always the question about costs, right? How many components do I need to add? And the less components I need to add to filter, then the more cost effective will be my filter in the end. So that's what I did for the differential mode. And for the common mode, we have to find, of course, another way of filter, and these are the so-called, I forgot to mention, these are the so-called CX capacitors. That's how you call them if they are between P and N. And for the common mode, we add the so-called CY capacitors. So you see this is a different filter, and we have this capacitor to ground from both lines. So basically you place a capacitor at the filter in between the P line and ground and between the N line and ground. Again, these are different values, typically smaller because you need to filter a higher frequency band. So this capacitor will be typically smaller than the CX capacitors. I have 22 nanofarad, 0.1 nanohenry, and 0.1 ohm here. And you see this setup doesn't change anything at the common mode, at the differential mode, excuse me. So the differential mode is completely unchanged with the CY capacitors, while the common mode is significantly reduced and only at higher frequency simply because of these values that I have selected here. Also, a second option, what I'm not showing here, is of course the use of common mode choke. And it's also a typical way where you put in a common mode choke to suppress the common mode. It's a choke which is wound in opposite directions and having a large common mode impedance. Sometimes, as I would say, a last resort, you can of course use ferrite clamps to clamp onto your wires. But I would say the first aim would be to first define the proper filter, and a ferrite clamp should only be seen like kind of last minute fix, and it's adding weight to the cables. It's also not it's also quite cost intensive. So clamps are, let's say, are countermeasures which are really your last hope or your last resort. So summarizing the filtering I have used, so you have seen that's also, now this table makes clear why I have chosen the separation in the differential and common mode, right? Because for the differential mode, you have a different way to filter than for the common mode. So for the differential mode, we have a CX capacitor or an inductor, while the inductor might generate some mode conversion. For the common mode, we have the CY cap, a common mode choke, or a ferrite clamp, which you have. So understanding how the emission, what is the properties of the emission you are measuring of your inverter, can always give you a good understanding which countermeasures will be needed. So you can simply, even if you have measured this, of course I'm using only simulations, but even if you have measured the emission, you can take the two spectrum for your both listen, add them and subtract them, and see, is it common or is it differential mode dominated, what you have measured. And from this understanding, you can choose the right countermeasure to implement into your system. So I did everything on the schematic up to now, but now let's take a further step. Of course, we want to simulate the real structure, the physical implementation, and not only just the circuit. And that's what I did. So I built a very simple model. So we have the typical table, metallic table with the both listens on top of it, and then we have a metallic enclosure with a very simple board. Here on the left-hand side is the input of the board. So you see this filtering components that I mentioned before. So CY, CX, inductor CX, basically they have been implemented. Here as ports, I will show you how I do the simulation later on. And I built a simple inverter. So it's a very simplified version, but it's a three-phase inverter. So basically here's the plus, here's the minus, and then the inverter, which is the three lines going out to a simplified motor. So I don't include the motor as a 3D model. That can be done, but it's challenging. You have typically a very complex model in the end. So I have the motor here with the three phases, and also the possibility to add a capacitance of the motor towards the enclosure here. And then this enclosure of the motor is connected via also PE to the enclosure. It's not connected to the enclosure, it's connected to this yellow part, which is actually the PE on the board. So that's how the model looks like. And now, when I have introduced the common mode, I was speaking about this capacitance values to ground that can be that are made an educated guess, right? But of course, we don't want to guess. We want to use the simulation to calculate realistic values, and that's the first thing you can do with a simulation, with a 3D simulation, and it's a very simple step which I use to start here. Is we calculate the capacitances of these two boards. So I told you there's a capacitance from the P line, from the plus going into the inverter, and from the N line, basically on the output of the inverter, and that's exactly red is the P line, blue is the N line here built as a PCB structure, and I can calculate the capacitance of these two metallic plates towards the enclosure. As shown here, the enclosure is in green. And when I run the simulation, the capacitance simulation is typically using electrostatic solver. It's very fast. So this is run in less than a minute typically for a structure like shown on the left hand side. You see then I have estimated 36 picofarad for the capacitance of the ground, of the blue to green, and 7 picofarad of the red to green. So it's not that far away from what I did in my educated guess, where I used 12 and 3, it's 36 and 7 are the more actual values. So that's a first and simple step how to employ 3D simulations. And what is often done in power electronics, actually, that's all of this parasitics, the parasitic to the enclosure, the parasitic of every signal trace, the parasitic of the cables, and so on. They are estimated by a simulation, or they are estimated by some best guess value, by some measurement. And then step by step, these parasitic values are put onto the schematic. As I have done before, I had the schematic of the inverter, and now I'm adding this simple parasitic values for the power cables, for the top side of the PCB, for the bottom side of the PCB, for the motors, and so on. It's something that people do for many years, and it's a valid way, of course, and we can do this also with CST Studio. We have the so-called partial RLC solver, so you extract basically RLC models from your geometry. You can export these RLC models at SPICE and put them on your schematic. Of course, at some point, this is becoming complex. You have a lot of parasitics. You're trying to put all the parasitics that are present in your setup, and you're trying to put them on the schematic. There is one big drawback that I see in this setup is you have to know which parasitics you have to include, because you're doing this manually, right? You say, okay, there is a capacitance between this line and the enclosure, so I will place this capacitance on the board. And this is something which really you have to be aware that there is a coupling happening, and estimate the value for the coupling and put it on the board. Which an experienced person will of course be able to do it. He will know which couplings are there and he will place it. But sometimes if you overlook something, you will not have it in your circuit, and you will not see these effects of possible couplings which happen inside the real structure, right? So it's a good way. What's of course the advantage here, you clearly see where are the couplings, and you can remove them one by one and see how much they affect. So that's something which people are used to do. But I propose a different way for today, and that's by using a fully coupled simulation, using a full wave solver, as we say in the simulation, using a fully coupled 3D simulation with schematics. So what we do, this is our approach. I think I'm propagating this approach already for a number of years. So the 3D solver is calculating the full structure, and everywhere where I would like to connect a component, I use a so-called ports. These are all of these red cones that you see spread over, because that's where I will connect my circuit, right? I still need the circuit of the inverter, the transistor models, the listen, and so on. I put them on the schematic, but the 3D structure, so basically the coupling between all these connection points, the coupling between the component, the parasitics due to the interconnects, they are no longer represented by an RLC model, because RLC models have their limitations in terms of frequencies, right? Once you reach some resonant behavior, the RLC model can no longer describe it, a simple RLC model. Of course, you can do a laddered RLC model, you can make it more complex, but you are at some point limited in the frequency. While when you use S parameters, you don't have this limitation. The S parameters is basically like kind of black box model. So what I get is a black box model described by S parameters, which describes all the coupling between the different ports in my setup. And this black box model is exactly this box here. So this is the box which has now information, which holds the information about all the possible couplings which can happen between the components, all the possible parasitics. And I attached my simulation model of the inverter to this box. So you can see it's looking a little bit different. There's a way how this ground is interpreted. I don't want to go into these details, but basically I'm connecting just the components as I had before. I'm connecting these components to this black box, which contains the information about the couplings. And what's the additional advantage of this is we will see, because when I do this coupling of the simulation model to the schematic as I've done here with the black box, I'm keeping the 3D model and the circuit connected, and it allows me to not only see circuit results, it also allows me to see field results in the 3D model, because the circuit can pass back information into the 3D model and really visualize currents and fields, E field, H field, current, basically under working conditions of the inverter. And that's something which you don't have in the previous approach, because in the previous approach you have only a one way. You extract values in the 3D model, you place them on a schematic, and you evaluate the schematic. While in the approach I'm showing here, using the full 3D simulations and the S parameters, you hand over the S parameters back to the circuit calculates basically the operating mode, and then the circuit can hand over the information from the operating mode back to the 3D model and allows us to visualize things. I will show you this in a few minutes. Of course, this simulation again done, of course, with CST Studio. Actually, you have a number of different solvers in CST Studio for the 3D simulation, but I choose the frequency domain method because that's typically the best choice for rather low frequency application. We are in the kilohertz range. And also for having this many ports, the frequency domain approach is more efficient. So if I do all the steps like I described before, what I get is also a emission spectrum, right? And I get this spectrum from this coupled model, and now I'm comparing the spectrum from this coupled model to the spectrum I have calculated with my pure schematic model, where I did some of these assumptions of the capacitors. And what we see on the left-hand side for the differential mode, you see that my pure circuit model that I did, it was by far not perfect. I did not include all the parasitics. But you see something like 500 kilohertz, my standalone circuit model, and the full model, including the 3D structure and the schematic as proposed on this slide. As this full model, which includes all couplings into a black box, up to 500 kilohertz, they actually agree pretty well. So my circuit model was fine up to 300 to 500 kilohertz, but above there you see that the 3D model is delivering a much higher emission than my simple model, simply because it includes all the parasitics which are in the structure which my circuit model did not do. So that I think a great cross-check to see, of course, the circuit model is valid, and the more parasitics you have, the higher you will typically push this agreement, right? So, but something like 10 or 20 megahertz is a very realistic value to which such a circuit model with parasitics works well. Everything above, when you move towards 100 megahertz, you typically will not be able to build a good parasitic model for that, and then your S parameter description is the only way to work with. And the same what we observe on the left-hand side for the differential mode, it's also true for the common mode. You see, also again, something like maybe here it's 300 megahertz, they agree very well, while then the 3D model, including the schematic, shows just a high emission because it considers all the parasitics, and the parasitics at the right values, right? In the beginning, I was just guessing these parasitic values. So that's the first important step. When you do this coupled model together with S parameters, you have a much wider frequency range in which your model is valid compared to a simple RLC model. And then additionally to this wider frequency range, of course, there is this visualization. As I have mentioned, we can take now the results from the circuit and feed them back into the 3D solver. And that's what I did here. So what we see right now is the current at 300 Hertz. If you remember, the 300 Hertz is the sinusoidal current going from the inverter to the motor. So basically the frequency of 300 Hertz is created by the switching of the inverter, and that's exactly what we see here. You see, I mean, the DC supply comes in here at the bottom left, goes through the filter. Here's the DC link capacitor, and here's the inverter, and it's the inverter that creates the 300 Hertz, and that's exactly what you can see here. I mean, there are some small values here, but here in this arm, the 300 Hertz signal does not flow. It flows to the motor, and that's exactly what you see here. It's the three-phase 300 Hertz 120 degree phase shift, as you would expect. That's exactly for which you have designed the inverter together with the PWM. So this is just as a cross check. You see, it generates the right field distribution, and when it becomes interesting is, of course, what's happening at the frequencies much higher, what's happening with the harmonics, right? So this is why I plot now 20 megahertz, and you can see that the inverter is generating, of course, a noise at the 20 megahertz. Of course, the value here of the current is much smaller than 300 hertz. At 300 hertz, it's a high current because that's the current you want to feed the motor with. But still, at 20 megahertz, there is a current, and there is a distribution of the current. And you can see, of course, the 20 megahertz, they don't flow to the motor. They are, I mean, there's a big portion here at the DC link. So basically the current loop closes between the inverter and the DC link. But also you can see that one of the CX caps here is contributing a lot to the filtering of this 20 megahertz because it closes the current loop of the 20 megahertz at this CX capacitor. And that's the way how you can use this kind of coupled or this resulting field distribution, resulting current distribution to debug your system. You see where the currents at this high frequencies flow. So if you have a certain problem at a one particular frequency, use the field monitor and visualize the current behavior. It helps you a lot in understanding, and it's something that a standalone circuit simulation with parasitics just cannot deliver to you. Only the full coupled simulation of the full wave together with the circuit, where we keep the circuit and the 3D simulation in one model. Only with this setup you are able to generate these plots, and they can be very, very helpful in understanding how, for example, resonances in your structure are generated. So one last thing, how, of course, when we have the RLC circuit, we might play around with the RLC values and see how it behaves. In a black box model, you cannot go there and modify the black box model. What you can do, of course, you can modify the 3D model itself, right, and rerun the whole thing. The simulation is completely coupled inside CSD Studio, so You hit the button, it first calculates the circuit, it first calculates the 3D model, then handing over data to the circuit. Circuit simulation is running, handing back the data to 3D. That's all automated. That's all running after you have set up the model with one button press. And this allows you now to, instead of looking at RLC, looking at your geometry actually. And that's what I did here. So I took the CX capacitors, which were, CY capacitors, which were connected here at the input, and they were connected to this yellow line, which connects to the enclosure. This is our PE. So you can see these two CY capacitors. I made them symmetric. So before they were going here to the left, both, and now I added a second piece of metal for the CE, which connect downwards to PE. And I placed these capacitors now symmetrically and rerun the whole thing. And it shows me like making this arrangement more symmetric gives me already something like a 10 dB improvement in the common mode, simply because I made it more symmetric, right? So this is the way how you would use then such a coupled simulation. Instead of thinking in RLC, think really in your geometry. If I modify the geometry, what output will I get? And that's exactly what I've done here. And I mean, 10 dB does not look much in this plot, but if you ask an EMC engineer, that gives if you give him 10 dB at zero cost, I've just moved the capacitor, he will take it for sure. So of course, this was a simple model. We can import more complex models. We can simulate pretty realistic things. That's not a problem, but I think the simple model was a good example just to demonstrate all the steps and demonstrate the ideas behind the EMC simulation. So what we did in the simulation is often not a competitor to your measurement. So you should use always simulation and measurement as a team. So both have advantages and both have disadvantages. I mean, the advantage, of course, of simulation is being able to visualize things, being able to run parameter studies like I did. I mean, moving the capacitor, making this capacitors more symmetric takes me something like 20 minutes. In measurement, you would need to order a whole new PCB layout, which would be much more time consuming. On the other hand, with measurement, of course, you can get a good idea of your component values. If your manufacturer doesn't provide component values for you, you can measure the component and use the measured values directly in the simulation. You can load a measurement and use the circ, for example, of a capacitor, the measurement of a capacitor. You can load it, put it on the schematic and use it. And of course, you should always make sure that your simulation is somehow validated with your measurements. So for the first projects you are doing, you need to do simulation and the measurement step by step. Once you know how your components behave, once you know some particularities of your transistor switches and so on, then it's the next step to use the simulation, of course, in a predictive way for future setup. But first, in the first project, even as painful as it is, you should make sure that you do step by step validation of your simulation with some measurement results. Once you did this once, you can bring the information you got there, you can bring some of the components model at a later stage and use the simulation at a much more early stage in your design. So that brings me actually to the summary. It was almost 45 minutes, so I had some fun speaking. I showed you how to analyze conductor emission from the motor inverter. Of course, the switching of the transistors will be your noise source number one. I separated them into a common and differential mode simply because to show you that each of them is using different type of filters. And then I showed you how to do all the simulation. I hope you could understood the difference between a RLC model and pure schematic and the fully coupled model with a full wave 3D solver and the circuit. I showed you how the current can distribute on a typical board. And I also showed you how the positioning of the filter elements can play a significant role. So that's brings me to the end. I hope you have enjoyed today's video. It's quite long, but I think valuable to look into if you're interested in the EMC simulations of inverters. So have a good day. Don't forget to hit the like button and subscribe, as they say on YouTube. Bye bye.